This video was created as a project for Introduction to Machine Learning course at the University of Siam, Vietnam National University, Ho Chi Minh City. We are continuing Phú Hòa, Phú Quý, and Linh. Together, we will summarize Beyond Self-Driving, an ICCV 2025 tutorial from the UCLA Mobility Lab and connect its 5 parts into one story. Imagine a smart car equipped with the latest AI. It perceives its surroundings in real time, reasons about what it sees, and makes split-second decisions. But here is the fundamental problem. Even the most intelligent single agent is blind to what it cannot physically see. A truck parked at the corner, a pedestrian hidden behind a wall. No model, no matter how powerful, can see through obstacles. Now add a second vehicle with a different vantage point. Suddenly the hidden pedestrian is visible. What one agent misses, another agent catches. This is the core insight behind cooperative perception, not making one agent smarter in isolation, but enabling multiple agents to collaborate. That's the thesis of this tutorial, so we taught them to cooperate. The tutorial unfolds in 5 parts. Part 1 asks why foundation models matter for autonomous driving and how they address its hardest problems. Part 2 explores how multiple agents fuse information across space and time. Part 3 grounds everything in real hardware and real-world deployment. Part 4 addresses efficiency such as data, training, and inference. Part 5 zooms out to the broader frontier, physical AI that operates safely in a world shared with humans. We begin with the models that bring broad world knowledge and general purpose reasoning into autonomous driving. Part 1 asks a simple question. Can foundation models help autonomous vehicles reason beyond the situations explicitly covered by their training data? Here is the tension that motivates this entire part. Since 2020, generative AI has made extraordinary progress. GPT-3 appeared in 2020. Clip and Dolly followed. ChatGPT arrived in late 2022 and changed the public perception of what AI could do. GPT-4 in 2023, Gemini, Llama 3, and models that see, reason, and converse simultaneously. The timeline is relentless. So why in 2025, with all of this capability, have self-driving cars still not spread everywhere? That question is exactly what we need to answer. To answer it, we first need to understand what a foundation model actually is, and what makes it fundamentally different from the task-specific models that autonomous driving has used until now. A foundation model is trained once on broad, large-scale data, and then adapted to many downstream tasks. The data can span text, images, speech, and 3D signals. Pre-training compresses these modalities into a shared representation rather than building an isolated model for every task. That shared model can then be adapted for information extraction, object recognition, instruction following, question answering, and many other applications. Before we can understand how foundation models change autonomous driving, we need to understand what autonomous driving systems look nowadays and why they have stalled. 3 system architectures have emerged over the past decade, each representing a different set of trade-offs. The dominant deployed architecture for autonomous driving is the modular pipeline. Perception identifies objects and classifies the environment. Localization places the vehicle on the map. Prediction forecasts the future trajectories of other agents. Planning decides what the ego vehicle should do. Control executes that decision. This pipeline is interpretable and easy to debug. Each module can be tested independently, which is why it dominates commercial systems. But it has 3 fundamental weaknesses. Errors accumulate from module to module. No joint optimization means each module pursues a local objective that may conflict with others. And the system cannot learn continuously from new experiences because each module is trained and frozen separately. End-to-end systems replace the entire pipeline with a single neural network. Sensors go in, actions come out. There is no handoff between modules, no error accumulation, and the system can be optimized jointly for the final goal. The cost is interpretability. When an end-to-end car makes a mistake, it is very difficult to diagnose where reasoning went wrong. Safety verification in a black box is a fundamental research challenge that the field has not yet solved. Hybrid architectures occupy the middle ground. Machine learning handles perception and high-level planning where it excels. Classical, verifiable control modules handle the actuators, where reliability matters most. Many leading companies are converging on this design because it balances learning-based adaptability with engineering-grade hardware guarantees. But all three architectures share a common weakness. Foundation models will make that weakness visible. Look at 3 real images from public roads. First, a person standing in the middle of an active lane, phone in hand. Is the car still moving? Are they even aware of approaching vehicles? Second, a truck on the highway carrying 3 traffic lights, upside down. Will any detection module classify them as irrelevant? Third, a road buried under deep snow, lane markings completely invisible. Lane detection fails entirely. These aren't constructed hypotheticals. They are the long tail of the distribution, rare events that are outside the training data of any system trained on standard conditions. 99% of driving is uneventful, but accidents happen in the 1% that looks like these 3 images. No dataset is large enough to enumerate all possible edge cases. The system needs another way. Why can human drivers handle these situations? Because we have contextual reasoning built over a lifetime of experience. We understand intent, physical causality, and social norms. This is what autonomous systems lack, is that foundation models are the first technology that may actually supply it. We need common sense reasoning and generalist experience to handle new domains and the long tail. Here is the connection between the foundation model ecosystem and autonomous driving. On the left is the foundation model ecosystem. Their shared world knowledge empowers the capabilities on the right. Auto-labeling, scenario generation, sensor simulation, vehicle interfaces, language reasoning, and end-to-end driving. Foundation models do not replace the autonomous driving stack. They strengthen it with reusable knowledge, with the goal of long-tail generalization and more generalist driving experience. Since 2023, researchers have explored 4 ways to integrate language models into driving: generating textual actions, producing numerical waypoints directly, providing high-level guidance to a separate trajectory planner, and transferring representations learned through language to downstream driving tasks. The key insight: language is not just a channel for human-issued commands. It serves as an interface for contextual understanding and reasoning, a way for the model to articulate why it is making a decision, not just what the decision is. That articulation creates a strong inductive bias toward generalization. To train these systems, new datasets were necessary. Drive LM chains language through perception, prediction, planning, and trajectory, forcing the model to explain each step. Kovli and impromptu VLA annotate real driving video clips with both trajectory data and language commentary. The result is a training signal that captures not just what happened, but why. BEV Driver encodes LiDAR and camera data into a bird's eye view map, a unified top-down spatial representation of the environment, then feeds that representation into a large language model for waypoint prediction. The approach combines principled 3D geometric reasoning with the world knowledge and language capabilities of the language model. The BEV encoding bridges the 2 domains: spatial structure in, language reasoning through, trajectory out. EMMA, end-to-end multimodal model for autonomous driving from Waymo, takes the most ambitious approach yet. Built on Gemini, the entire pipeline runs through language tokens. Raw camera frames arrive as input. The model produces a chain of thought. It first describes what it observes in the scene, then reasons about what other agents are likely to do, and only then commits to a trajectory, alongside structured outputs for object detection and road graph prediction. Drive VLM from Tsinghua takes a dual system approach. A vision language model operates at low frequency handling scene, understanding, and high level planning, where language reasoning adds the most value. In parallel, a traditional 3D perception and trajectory planning module runs at full real-time frequency, handling the fast, safety-critical control loop. The design combines the reasoning power of language models with the speed guarantees of classical modules. The trade-off is significant engineering complexity, but it is currently one of the most practical paths to a deployable VLA system. Previous VLA models had two related problems. First, generated action sequences were often physically infeasible. The model didn't learn the geometric and dynamic constraints of real vehicle motion well enough. Second, reasoning was always slow. The same chain of thought computation happened regardless of whether the scene required it, creating unnecessary latency. Auto VLA from UCLA addresses both with a dual thinking mode design. In fast mode, the model outputs an action directly when the situation is routine. In slow mode, it activates a full chain of thought when the scene is ambiguous or complex. This mirrors what cognitive science tells us about human decision-making. Routine routes run on near-automatic processing. Unfamiliar or high-stakes situations trigger deliberate, effortful reasoning. Results on the new plan and new scenes benchmarks show a consistent finding across all four evaluation metrics. Reasoning augmented training outperforms action-only training. Teaching the model to think well makes it act well. This is not circular, like the reasoning is evaluated separately from the action, so the improvement is genuine. 4 takeaways from this part. Foundation models open the long-tail systems that understand the world rather than memorizing rules, can reason about situations never seen in training. Multimodal LLMs are the leading architecture. They bring out-of-domain reasoning, internet-scale world knowledge, and interpretable reasoning chains to a domain that has historically resisted all three. There is no dominant paradigm yet. Dual system, unified end-to-end, BEV encoding, RL fine-tuning. The field is in active exploration, which is a sign of genuine intellectual progress, not stagnation. Foundation models are not a complete solution. Safety verification, interpretability, and formal guarantees remain open problems. Compute cost and latency are still real barriers to deployment at scale. Foundation models may address the long-tail problem, but there is a physical limit that no model, however capable, can overcome alone. That's the subject of part 2.